Welcome to the University of Oslo and the Semiconductor Physics group. We also call this group LENS, abbreviating light and electricity from novel semiconductors. This is because we are motivated by big questions like how to solve humanity's ever-increasing need for clean energy. In particular, we are very interested in materials for solar cells, but also LEDs and other electronics, as these are based on the same material properties.
Working as a semiconductor researcher implies a lot of experimental lab work. We work at the Microsystems and Nanotechnology Laboratory, where we have access to a wide variety of instruments and machines.
Working with semiconductors requires a very clean environment, so we need to do all synthesis inside a well-controlled clean room. Let's take a closer look at an ongoing project.
In this project, we want to be able to control the bandgap of the alloy system zinc oxide with gallium nitride. The bandgap is a material property that affects the electrical and optical behavior. To obtain optimal growth conditions, the sapphire substrates need to be cleaned before deposition. We synthesize zinc oxide thin films with increasing gallium nitride's content. The deposition takes place in vacuum by magnetron sputtering at a rate of about 1 nanometer per minute. Defining the energy of light that can be absorbed or emitted from a material, the bandgap is the most important property of many optoelectronic devices, including solar cells. On the atomic scale, it is the composition and structure of the material that determines the bandgap.
After some depositions, we see that the samples appear very different depending on the gallium nitride content.
A more thorough investigation than just looking at the sample is necessary. We can measure the optical bandgap and absorption properties by doing spectrometry in the visible and the ultraviolet region. For the darker samples, with higher gallium nitride content, we observe a systematic decrease in bandgap energy. Ideally, the alloy should crystallize in one structure without the precipitation of secondary phases. This should be possible to achieve considering the similar structure of pure zinc oxide and pure gallium nitride. To investigate the crystal structure of our thin films, we analyze the measured X-ray diffraction patterns.
Now that we are able to control the bandgap in these films, we can continue to investigate how this bandgap reduction affects other material properties. These properties are all important to understand when developing a material and devices. This is just one example of a project that we're working with at LENS. If you too want to take part in developing the energy conversion materials of tomorrow, come join us.